he can also calculate when q is a half. Because it doesn't matter what q is, he can calculate that. So he calculates those, and he puts those numbers in. And I have them marked in blue. Okay? And now he cannot, however, calculate anything with p equals a half, or 3 halves, or 5 halves. Those he simply can't do. But he can get some of them now by the symmetry. So he's now able to fill in those yellow spots from integrals that he cannot calculate, but follow from the symmetry assumed in the table. Okay, so he's able to do that. Then he goes on, and he says, okay, now how did these numbers come about? He looked at those numbers, and then very cleverly, he sees how they grow. So he notices that the number that was here and the number that was here grows in a nice way in which they grow. The number that's here, and then see how that is extended, and how that is, see that? He sees patterns, and he writes those patterns down now. And by the way, comment on these patterns. Remember, these are binomial coefficients. And the formula for binomial coefficients we usually associate with Newton as having discovered that when he wrote his famous letter to Oldenburg, the Secretary of the Royal Society, describing how he derived the binomial coefficient for fractional exponents. Okay. Well, when he wrote in that letter, he attributes the ideas to Wallis. And he sure should. There it is. There's the formula for binomial coefficients. Okay. Apparently, Wallis doesn't notice it. Or at least he doesn't say anything about it. Maybe he just figures it's a distraction and he doesn't want to say any more. But there they were in Wallis. Okay. But Newton does credit Wallis. But Wallis actually had the whole thing. Okay, anyway. All right. So now he says, okay, I know this number. I see a pattern how these go. See, they all have the same denominator, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. And the numerators grow 1, 2, 3, 4, like that. Okay? Now, can I figure out a way to get these numbers by filling in between? He says, well, that's not going to be easy because to go from 1 to 2, you need a half over here. He doesn't like that. So to fix that up, he doubles all the numbers so that he won't get halves. So he multiplies all the numbers on top by 2, numbers on the bottom by 2, and then he gets this, okay? And now, so now instead of having 1, 2, 3, he has 2, 4, 6. And now the top goes 2 to 4. Aha, now he can put a 3 there. And see what happens. So he's going to interpolate between these two expressions and see what he gets. And if it equals this, which he already calculated, he knows he's right on. He's got it. And in fact, of course, it works. It gives him exactly the numbers that he knew should be there. And so he now knows that he's really onto something. He's got the patterns going. Okay, he's into the patterns now. Okay, and then so finally now he's getting close to 4 over pi. He's filled in almost everything. He sees a little more, and he conjectures. A lot of it's guessing. Well, so much guessing here. Starts guessing at the way these go.
Nowadays it's called experimental mathematics.
Yes, of course, it's experimental mathematics. That's what's always been going on, right? It's nothing new in that sense. The only thing new is you're using a computer. Their computer was their head, and a quill pen, and paper if they could get it. So, okay, so there he is, and now in the final step, what he does is he starts looking at the ratios of these. the ratio of this to this, the ratio of this to this, the ratio of this to this. And when he studies those ratios, he discovers that as you go out in the row, the ratios approach 1. And then he unfolds that, and he has his product. That's how he gets it. Now, when he's studying that ratio, what is he doing? He's taking the ratio of two integrals, two beta integrals. See? That's where the formula that Euler used came from. And you can see the idea for it is right there. Okay, are we doing here? Okay. Okay, so we don't want to go anymore. Okay. Now, finally, show you one more thing here. If we go back to the continued fractions, here we go. If we go back to the continued fractions of Brouncker, you'll notice that we have these started 1, 3, 5, 7. Okay. Well, what about 2 and 4 and 6? What about them? Okay. Well, it turns out you can get them also from the from that formula that had the 4 gamma functions equals the continued fraction. And so I studied those recently, and I'll show you what that leads to. That leads to the Lemniscate constant. What is the Lemniscate constant? The Lemniscate is a curve that looks like a figure 8. Okay, it looks like this. This is the 1. And this is its formula. R squared equals cosine 2 theta, polar coordinate formula. And if you go and do the usual calculus arc length and take half of that, half the arc length, you get this number that is usually called L. And it turns out that you get it in terms of gamma of a quarter squared, and also pi. It's this. So half the arc length of this Lemniscate is L, the Lemniscate constant, just like half the circumference of a unit circle is pi. And it's not surprising that the two numbers sometimes appear in similar